Hi, my name is Christopher Schulte, and today we'll be talking about lab number 3, the topic of a black hole and curving motion. The purpose of the lab was to observe the motion of a star with a unique trajectory to find the net force on it for all points in the dataset using a computational model. Then using the generated data, we are to determine the mass of the black hole which the star is orbiting. Using these values, we are then to determine the necessary initial velocity required for a spaceship to launch from a nearby orbiting planet without crashing into the planet or the black hole. The goal of the lab was to utilize physics principles and the computed data to determine the mass of the black hole, then determine the initial velocity required for a spaceship to get close enough to the black hole and leave the system without crashing. The fundamental physics principles and models used in this lab included Newton's second law, which states that the change in momentum is equivalent to the net force times the change in time, which can be written as the net force parallel plus F-net perpendicular components times the change in time. The F-net parallel represents the change of speed of the object, while F-net perpendicular is responsible for changes in the direction of the motion. The total net force is equivalent to F-net perp plus F-net plus F-net parallel. On the left, we see a graph of a problem involving the net force of a circular motion, in which is broken up into F perp and F parallel. As well, we use the gravitational force, which states that gravitational force equals negative g m1 m2 over r squared times r hat, where g is a gravitational constant and r represents the distance between the two objects. Overview of results. For part 1, we see that the system is orbiting the star, while the surroundings is the black hole. For part 2, the system is the spaceship and the surroundings is the planet and the black hole. Results. The determined mass of the black hole is 1.72 times 10 to the 34 kilograms. Using this value, the determined initial velocity for the spaceship, such as not crash into the planet or the black hole, is negative 6.5 times 10 to the 7th, 3.5 times 10 to the 6th, 0 meters per second. Data and analysis. The initial conditions, we have a gravitational constant, the mass of the star, which is 2 times 10 to the 30 kilograms, and the time interval between data points, which is 1 day or 60 times 60 times 24. In our computational model, we see that we start by computing the initial and final momentum vectors, where momentum equals mass times velocity, and then we calculate the star's change in velocity and change in momentum using the formulas delta v equals vf minus vi and delta p equals pf minus pi. We can then calculate net force utilizing Newton's second law as we saw in the last slide, and from there we can calculate F-net parallel and F-net perpendicular, where F-net perpendicular equals the total net force minus F-net parallel. We can then use these values to calculate the mass of the black hole using the formula m equals dp dt times the magnitude of r squared divided by gm, where capital M is the black hole mass and little m is the mass of the star. Here we see a generated visual of the orbit, and we determine that the mass of the black hole is 1.72 times 10 to the 34 kilograms, and as we see, we have a while loop, so therefore this is calculated by taking the average over the calculated mass at every iteration. We also have the magnitude of F-net, F-net parallel, and F-net perpendicular here. For part 2, we asked to find the initial velocity of the spaceship. We have the same initial conditions, except now we know the mass of the black hole, so that is seen here. And then we also have a while loop in this scenario. We started by knowing that F-net equals the gravitational force of the black hole plus the gravitational force in the planet, and these are the two only forces acting on the system. We first calculated a net force on the planet, as seen here, and then the net force on the spaceship. And then we added these two to get the total net force. At the end of our while loop, we used the position and velocity update formulas as derived from Newton's second law to update the position and velocity of the planet and the ship at every time interval. Using trial and error, we determined the initial velocity to be negative 6.5 times 10 to the 7, 3.5 times 10 to the 6 meters per second. And here's a generated model of the system in which we can see the spaceship passing the black hole but not crashing into it or the planet. Conclusions. Some key takeaways in physics principles used included identifying the system and surroundings, using a computational model and iterating, then utilizing Newton's second law and various derivations along with circular motion to determine the net force and parallel and perpendicular components, then the gravitational force and application to determine the net force of the system at hand. Some possible sources of error included inaccurate approximation of the mass of the black hole. Since the computational model utilizes the while loop or iteration, the calculated mass of the black hole was determined by averaging the mass at each iteration. This could be slightly different than the actual mass of the black hole, which was used in part 2 of the lab, meaning there might be a slight error in the initial velocity of the spaceship so that it does not crash into the planet or the black hole as well. What does it mean? Net force is the overall force acting on the object, taking into account or adding all individual forces. The parallel component acts in the direction of the object's velocity and can speed up or slow down the object depending if it's acting in the same or opposite direction of the velocity. And the perpendicular component acts perpendicular to the object's velocity. This component can change the direction of the object's motion without affecting its speed. The rate of change in momentum refers to how the momentum of an object changes over time. It is equal to the net force acting on the object according to Newton's second law. Its parallel component represents how the object's speed is changing due to the net force, while its perpendicular component reflects changes in the direction of motion without affecting the speed. What if? The initial velocity calculated for this section is negative 3.7 times 10 to the 6, 5.4 times 10 to the 6 meters per second, and this accounts so that the spaceship enters into an orbit and it does not crash